Hello, Applied Physics students. Here is your corrections for the homework assignment that's assigned from pages 81 to 83, 9 through 11, 17 through 19, 20, 24, 27, and 30. Number 9 says, at the instant a ball is thrown horizontally over a level range, a ball held at the side of the first is released and drops to the ground. If air resistance is neglected, which ball strikes the ground first? So the situation is level ground. I have my ball. I'm going to launch it horizontally, and I'm just going to let it drop. And the question is, if air resistance is neglected, remember that means we're ignoring air resistance, which ball strikes the ground first? This is actually a trick question because they're going to hit the ground at the same time. And that's because, remember, the vertical component and horizontal component of velocity are totally separate from each other. And hitting the ground only has to do, with the vertical component. And the only thing acting on these two balls in the vertical way is the acceleration due to gravity, which is G. And it acts on them both exactly the same way, so they're going to hit the ball at the same time. Question number 10. How far, 10 has an A and a B, how far, letter A, how far below an initial straight line path will a projectile fall in 1 second? So the idea is, here's my projectile, and I have thrown it like this, right? And that's that straight line path. And the question is, how far below it is it going to fall in 1 second? Remember, when we figure out D equals G 1/2, D is 1/2 GT squared, the distance that something falls. So the time is 1 second, so we have 0.5 times 10 meters per second squared times our time, which is 1 second squared. So 1/2 of 10 is 5 times 1 squared is still 5. So it's going to fall 5 meters. So here's where the ball really is going to be, on its projectile path, and this distance is going to be 5 meters. Letter B, does your answer depend on the angle of launch or on the initial speed of the projectile? Defend your answer. So the question that's being asked is, does this depend on the speed here of my launch, or on this angle in any way, shape, or form? And the answer to both of those is no. And that's, again, going back to that same reason. The only thing acting on the ball in the downward direction is the acceleration due to gravity. Which is, we call it G. And so that's the only thing acting on it. So the person who wrote the textbook explained it this way. No, the vertical displacement below any line is 1/2 GT squared. So that's number 10. Number 11. Neglecting air resistance. If you throw a ball straight up with a speed of 20 meters per second, how fast will it be moving when you catch it? So again, here I am, I'm standing, and I'm throwing this ball, and right here it has a speed of 20 meters per second upward, and I put my hand out and I catch it when it's coming back down. Remember, this is that one where it doesn't take any math to prove this, because we've looked at this in a bunch of different pictures throughout this unit. That ball is going to return to that same height with the same speed. The difference is, because velocity is a vector quantity, when we throw it it has like a positive 20 meters per second because it's upward, and when it's coming back down, it has a negative 20 meters per second because it's coming downward. But it's going to be 20 meters per second. So the next question is number 17. Number 17 says, okay, the airplane is blown off course by wind in the direction shown. Use the parallelogram rule and rank from highest to lowest the resulting speed across the ground. So it might be helpful to have a picture of this. So let me see if I can get a picture. Oops, sorry, a picture of this in here. And we'll see how this goes. So, there we go. All right, so there's number 17. So remember, this is our parallelogram rule. So this is where we want to draw, like make our parallelogram. So we're going to draw, you would probably use a ruler, but we're going to draw parallel lines. And remember our resultant, which I'll do in my favorite color, orange, is the diagonal of that. So then we do this again for the next one. So again, we draw a parallel line, so it's kind of going like this. Oops, let me choose that better. That green we could see a little bit better, right? So it's kind of going like this. And then this one kind of goes like this. So my resultant here would be that. For my third one, okay, my parallel to this is going to look kind of like that, and then like that. So my resultant, okay, is right here. And then that last one, okay, parallel to the wind is going to look like this. And then parallel to the motion, and so my resultant is going to look like this. So the question was, we want to rank from highest to lowest the resulting speed across the ground, right? That ranking, I can tell by the length of my vector. So my resultant vector, which is in orange here, the length represents the magnitude or size of the velocity and the speed. So the longest line or arrow has the most speed. So if I have done this correctly and kind of carefully, the longest arrow is letter D. Next comes B, then A, and then C. And again, I can do that without math. I can just do it by carefully constructing my parallelograms and looking at those resultants. So that is number 17. Taking a look at number 18. 18 says, calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer per hour tailwind, if it encounters a 50 kilometer per hour headwind. So here's my airplane, right, with its wings. So this is my front and this is the back of my airplane. And if it encounters a tailwind, okay, a tailwind means that it's coming from the tail. So if my plane's velocity is this way and it's 200 kilometers per hour, the tailwind is going to go the same way. So this is my tailwind, and it's 50 kilometers per hour. So what that's going to do is that's going to increase the speed of the plane. the speed of the plane is going to be 200 kilometers per hour plus the tailwind that's helping it along at 50 kilometers per hour, resulting in 250 kilometers per hour being the speed of the plane. Okay? Now, if it encounters a headwind, the headwind means it's coming from the front. So now we have a 50 kilometer per hour, but it's a headwind. That means it's going to decrease because, again, these vectors are in opposite directions. And because they're opposite directions, we're going to find the difference between them. So 200 kilometers per hour minus the 50 kilometers per hour gives us a resulting speed of, just did my math wrong, of 150 kilometers per hour. So that's number 18. Number 19. Calculate the magnitude of the resultant of a pair of 100 kilometer per hour velocity vectors that are at right angles to each other. So I have one velocity vector that's 100 kilometers per hour, and I have another one that's 100 kilometers per hour, and they're at right angles to each other. So this is where we can use the Pythagorean theorem. Okay. Okay. And we can create, right, that figure out that resultant. That's 100. This is 100. This is a leg, so it's like an A. This is a leg, this is a B, and this is my C. So the Pythagorean theorem says A squared plus B squared, the length of each leg, equals the length of the hypotenuse squared. So if I want my resultant, I'm going to take the square root of the legs squared. So that's going to be the square root of 100 kilometers per hour squared plus 100 kilometers per hour squared, and then take the square root of that. So 100 squared is 10,000. So I have the square root of 10,000 plus 10,000. Okay. And then I'm going to take the square root. So I'm going to take the square root of 20,000. And I get 141.4, and my units would be, because it's a velocity, kilometers per hour. So that's how you do number 19. All right, our next one is number 20. 20. Calculate the resulting speed of an airplane with an airspeed of 120 kilometers per hour pointing due north when it encounters a wind of 90 kilometers per hour directed from the west. Recall, speed is the magnitude of velocity. All right, so we have our airplane, and it's going due north, so we're going to kind of draw that as straight up. And it's 120 kilometers per hour, and this is our plane. Now, we have wind, and it encounters a wind directed from the west. That means it's coming from the west. So if I kind of just use like north, south, east, west, it's coming from the west, so it's blowing east, and it's not quite as long. I'd probably make it a little longer than that, though. Okay. This is 90 kilometers per hour, and this is my wind. So the question is, what is the resultant? Okay, what is that resulting velocity? So again, this is where I'm going to use my parallelogram rule, right? I'm going to draw my parallel lines and draw in my resultant. Notice again, I have this 90, this is the same length here, so this is 90 kilometers per hour. This is 120 kilometers per hour. And this is that right triangle. So I can use my Pythagorean theorem to figure this out. So to figure this out, I want my C, which is the square root of 120 kilometers per hour squared plus the 90 kilometers per hour squared. And then I'm going to take the square root of that. So 120 squared is 14,400. 90 squared is 8,100. I'm going to add those two numbers together. So I'm going to be taking the square root of 220 or 22,500. So then I'm going to take the square root of that answer, and I get 150, and my units are going to be kilometers per hour. So the speed of this airplane across the ground is 150 kilometers per hour. Notice, even though my wind is blowing at a right angle to my plane, it still increases my plane's speed across the ground. That's number 20. Number 24. 24 says, how does the vertical distance a projectile falls below an otherwise straight line path compare with the vertical distance it would fall from rest in the same time? So what we're talking about is, let's say I drop my ball, okay, and my ball's here, and then here in the 2 seconds, and maybe here at 3 seconds, okay? So this is where it started. Now, let's say, though, now I throw this ball and I launch it at an angle like this. Okay? What that means is talking about is how far below this line would it fall each second. And that distance below that line is that same distance. So if that's my first one, then my next one's a little bigger, and my next one's a little bit bigger. So the answer to this is, okay, they are exactly the same. And again, that's how you get that projectile motion. That distance, if I launch my projectile like this distance it falls below, sorry, I should fix that a little. The distance it falls below this line in each second is the same as the distance it would fall in 1 second. And the distance it would fall in 2 seconds. And the distance it would be below that line in 3 seconds. So if I was good at drawing it, if this was 5 meters, this would also be 5 meters. If this was 15 meters, this would also be 15 meters. And if this was 25 meters, this would also be 25 meters. So they would be the same distance below. So that's number 24. Number 27. 27 says, how is the horizontal component of velocity for a projectile affected by the vertical? So what we're talking about here is when I throw this ball up in the air, okay, and I look at its vertical and horizontal components of velocity, how do they compare? Okay, now remember, we've talked about this a couple times, right? The horizontal is constant. It doesn't change. So if I were to draw this, I would draw the same length one. Now, the vertical component changes, right? So the vertical changes. remember, it is going to be affected by gravity. So, as that ball is moving up in the air, that vertical component is decreasing. So going back to our question, which was, how is the horizontal component of velocity for a projectile affected by the vertical? They're not, right? The horizontal and vertical do their own things. They're completely separate. So they are not affected by each other. The person who wrote your book said, not at all. Horizontal and vertical components of velocity are independent of each other. So that's question number 27. Our final question is number 30. 30 says, a projectile is launched vertically at 50 meters per second. If air resistance can be neglected, at what speed will it return to its initial level? If air resistance can be neglected, at what speed will it return to its initial level? So I throw this object, okay, and I'm throwing it straight up. And so the question is, after it's gone straight up and it's come straight down, and it gets back here, again, what speed will it have? Okay. Well, if I launched it over here with 50 meters per second, again, we've talked about this a lot. It's going to return to this level with the same speed of 50 meters per second. And then it says, where in its trajectory will it have minimum speed? Remember, that's right up here at the very top. Okay? So at the top of its trajectory. So I hope if you had some questions about the homework, that helps. Have a great day. Talk to you tomorrow.